Okay, kids, we're back here. Great question. Section 4.5, and it's practice question 16. A 120-gram mug at 21 degrees Celsius is filled with 210 grams of coffee. Coffee is basically water at 91 degrees Celsius. Assuming all of the heat lost by the coffee is transferred to the mug, what is the final temperature of the coffee? The specific heat capacity of the mug is 7.8 times 10 to the 2 joules per kilogram degrees Celsius. So the whole idea here is that whatever coffee heat the coffee had is given to the mug. So whatever heat is lost by the coffee is gained by the mug. And since it's a complete transfer of that, whatever is lost by one is gained by the other. When you add the loss of one to the gain by other, it has to equal zero. You can't give up heat and just lose it into the thin blue air if we're assuming that the heat transfer is direct, and you can't bring in heat from the outside. So the sum of the loss and the gain will give you zero. Whatever is lost by one is gained by the other. Another way of saying this is if I lose 10 bucks and you gain 10 bucks, I'm at negative 10, you're at plus 10. Negative 10 and plus 10 gives me zero. The sum between the two of us is zero. But what is the definition of heat? Well, it's equal to the mass of the, since it's heat loss, the mass of the hot material, the specific heat capacity of the hot material multiplied by the change in temperature, delta T of the hot material. And then here, plus gained, well, it's the cold object that's going to gain the heat. So it's the mass of the cold object gaining the heat, the specific heat capacity of the cold object gaining the heat, all times the change in temperature for the cold object, and that equals zero. Now, we've decided the hot object is the water, coffee. The cold object is the mug. Here are the specific heat capacities for these. For example, 7.8 times 10 to the 2 joules per kilogram degree Celsius. So it takes 780 joules of energy to change the temperature of 1 kilogram of the material that the mug is made out of by 1 degree Celsius. That's literally what specific heat capacity means. So then what do? Well, then we change delta temperature into what it means. The mass and the specific heat capacity stay the same, but delta temperature means final temperature minus the initial temperature that the hot water had. Similarly here, we keep the mass, we keep the specific heat capacity, but change in temperature means temperature final minus the temperature initial that the cold object had. Notice one thing here though, the final temperatures are the same. The mug will heat up, the coffee will cool down, and they will come to a common, the same final temperature. And it's always equal to zero. We haven't done anything on the right-hand side. Next, what we're going to do is substitute. So all the values are known, and we plug them all in. That's all I've done in this line right here. I've plugged in all of the specific heat capacities. So let's continue here. What do I do next? Well, I do some distributive multiplication. So I multiply this into here, and it gives me the 877.8. Notice, so something very important here. Notice the kilogram here cancels the kilogram here. All you're left with is joules over degrees Celsius. Same thing here. I do some distributive multiplication. I multiply that into here. And notice once again that the kilograms cancel. So all I'm left with is joules per kilograms, excuse me, joules per degree Celsius. There it is. So I multiplied in there. What do I do next? Well, what I'm going to do next is I'm going to divide both sides by 93.6 joules per degree Celsius to simplify this equation. So I went 877.8 joules per degree Celsius divided by the 93, that's a 9, 93.6 joules per kilogram Celsius, and the units completely cancel out. Look, joules over degrees Celsius, look here, joules over degrees Celsius. Units cancel out, and when I divide, I get 9.38. The bracket stays the same. And here I'm dividing 93.6 joules per degree Celsius by itself. So it's gone. I mean, there's a 1 there, but nobody writes it. And the bracket stays the same. What am I going to do now? Well, I'm going to do some more distributive multiplication. Multiply into here and multiply into here. And we have 9.38 temperature final minus 853.58 degrees Celsius plus, well, if you're multiplying in by 1, you're basically just removing the brackets, so that's what I've done there. What am I doing next? I'm collecting like terms. Here's a TF term, here's a TF term. 9.38 TF plus 1 TF gives me 10.38 TF. Here I'm collecting the like term that contains degrees Celsius. Negative 853.58 degrees Celsius. To that, we add a negative 21 degrees Celsius, and we get negative 874.58 degrees Celsius. What do I do next? Well, what I do next is I take this and I bring it to the other side, this degree Celsius term, and it becomes positive on this side. What do I do finally? At the end, I'm going to divide by 10.78 on both sides, and I have a final temperature right here of 84 degrees Celsius. So there you have it. Thank you so much for asking that question. Bye bye for now.